Let's start out with some questions for y'all.
Y'all.
Yeah, I like pretending like I'm from the South.
Very southern of you.
Raise your hand if you've heard of containers before. All right, that was an easy one. Okay, now raise your hand if you've used containers before.
Oh,
getting better.
Good.
Okay, raise your hand if you feel like you understand what containers do at a lower level, like how they work. Anybody? A couple? Okay. So we're here to talk about debugging containers and some of the tools that we've built around building and debugging containers in open source at Oracle. But we also want to spend some time discussing containers in general and explaining how they work, because there's some pretty fascinating stuff in there. So let's get started. First of all, let's introduce ourselves.
Oh, I'm TJ Fontaine, currently leading some of the Kubernetes efforts inside of Oracle. Previously, in a previous life, I was also the maintainer of Node.js.
And I'm Vish Ishaya Abrams. I spent a lot of time working on OpenStack. I helped create it at NASA. And I was the lead for the compute project for a long time. And lately I've been working on Oracle's cloud and containers specifically. So there's a lot of interesting things we've discovered over the past couple of years. So basically we're going to start out talking about what is a container and to clear up some misconceptions. And we'll just do this very briefly and talk about exactly how they work at a lower level, just to give you an idea of some of the complexity that underlies containers and can help you understand why we need to build tools around them. And then we're going to actually go through a demo of how you can build containers with our tools and debug them. And then hopefully some time for some questions and answers at the end, if there's anything interesting. Now, this is a small group, so I want to say right away, if you have questions, you might as well just interrupt. We can make this a discussion. I'm going to try and ask you some questions throughout this, just to make it hard. There won't be a test, but it's nice if it's interactive and we can have some fun talking about this.
There's no test, but we're grading you anyway.
Everybody gets an A. Okay, so what is a container? So one of the biggest points of confusion around containers is the term container is generally used to represent two different things. People talk about downloading a container off the internet. I went on to Docker Hub and I downloaded an Apache container. And they also talk about running a container. And these actually are two separate concepts that are the same word is used for. So a container can be an application bundled with its dependencies. And that's when you talk about downloading something from Docker Hub, you're talking about that form of a container. And another word for that, just to eliminate confusion, would be a container image. And then there's the running copy of that application that's isolated from other processes on the system. So containerization means isolating one process from other things that might be running on the system. Similarly to how a virtual machine would isolate some processes from other processes. So this little diagram kind of gives you an idea of how the basic container workflow works. So you start out generally with building an image. This can be done on your local machine, or it can be done by CI/CD, by a continuous integration system. So you have an application, and you do a build, and that gives you an image. Then you push that image up to a repository, usually, and then on your running host, where you're going to run the application, it downloads the image, and there can be more than one of these hosts where the image is going to run, and then it runs the image and turns it into a running container. So I've used these nice little box and truck icons to just help differentiate the idea of container image from a container. So an image is like a VM image. It's an immutable bundle. It's the application plus its dependencies. And the whole point of building a container, putting your application in a container, is to make it portable across different hosts. A running container can be thought of like a virtual machine. So it's protected from the other applications on the host via a few different things. Isolation of the owned resources, restricting the actions that the application is running in the container can perform, and limiting the access to shared resources. This is where the low-level container bits get in. So have you heard of Linux namespaces before? Yeah. So Linux namespaces is generally the way that you isolate processes. And this could be contrasted with something else, which would be FreeBSD jails or Solaris zones, which tend to isolate everything together. In Linux, it's piecemeal. You get little bits of isolation. You have to combine them all into one thing. This has advantages and disadvantages. The advantages are you can often do introspection from different parts of the system, and you can share certain parts of the system with other parts. So for example, you could have two containers that share one of the namespaces. But on the other hand, it makes it much more difficult to configure, and especially to configure securely. In addition to namespaces, often there's another layer of access control and isolation, another layer of isolation that's using built-in access control, either SELinux or AppArmor. Then in addition to isolation, you restrict the capabilities.
No,
Okay.
keep going.
You were looking really excited there.
I'm right here with you.
So basically, the process that's running in the container, you want to restrict what it can do when it's interacting with the kernel specifically. And there's various ways of doing that. One is to drop the capabilities of the process. One is to set the UID and the GID of the process to something that's limited. And the third is to restrict access to syscalls via something like setcomp, which is a recent thing that was added to Linux to actually filter certain syscalls. This is very important because a lot of the vulnerabilities in Linux happen around certain syscalls that aren't used very often. So it's nice to be able to limit it to just the ones that the container actually needs. And then finally, not everything can be isolated. So there's certain hardware resources in the computer. You have a disk, you have a network, you have CPU and memory. And these are shared resources. And so those have to be divvied up and controlled. And the way that that is done is through a Linux subsystem called cgroups. Cgroups covers most of the sort of limiting of the different hardware primitives underneath, but there are certain things that are not limited by cgroups and generally are done via another method. For example, filling up disk space, creating a denial of service by overloading a host daemon. For example, if you're writing to log the syslog a whole bunch, then you can overload the host, and controlling network bandwidth using quality of service. So generally, a container runtime will use cgroups for most of the stuff, but then have additional ways of preventing sort of denial of service attacks from one container to another on the host.
And one thing to keep in mind is that these resource controls are all focused in Linux namespaces around the user space process that's actually running. So there are also usually on the flip side, kernel resources that are associated with that, network buffers that are related, page files that all play into this as well. So those kinds of resource controls are necessary, but not sufficient. And there's been a couple slides that say containers are like VMs. That's just a means for us to describe them. They're not actually VMs.
Yeah, so you're sharing the kernel, and that's where you sacrifice a little bit of security, because the attack surface for the kernel is generally much larger than the attack surface from the VM virtualization layer, which is virtualizing hardware through a smaller interface. Okay, so that kind of covers what containers are. Does anybody have any questions on that before we move on? Okay. So the next thing to understand is generally when you're using containers, especially when you're building things like microservices, you don't just have the container, you have an orchestrator that runs the containers on different hosts. Yeah.
I mean, I worked with Unix quite closely, and like until 15 years ago. Is container only applicable on Linux, or can it be made available on other systems, Unix systems too?
The question is, are containers a Linux-only technology?
Not really. They aren't, but in most practical cases, that's where they're used. So there's also containerization for Windows, for example. If you try and run it on something like a Mac, then it tends to actually run on Linux behind the scenes. It could apply to other brands of Unix, although these days there aren't a whole lot of other Unixy brands out there.
Yeah.
So it's like based on how you described it, I'm new to containers. It seems like it's something which can be only made possible by dropping things within Linux, and you can't do that in, say, BSD Unix or Mac Unix. And Windows is not Unix. So
right.
Well, so history lesson I'll put on one of mine. Containerization for a large portion of it is really just a beefed up chroot. So if you're used to using chroot, that's like the bare minimum. So chroot in Linux terms, right, would be a file system namespace. And then there's a bunch of other namespaces that got built on top of that. So if you walk through the history of things, you have next FreeBSD jails, which took that a little bit further and gave you some more process isolation and network virtualization go on along with that. Then you have Solaris, which comes in with zones, which gives you even more OS virtualization to tackle all of those things. In Linux, you have a parallel history with technologies like OpenVZ and vServer, where they were starting to add these technologies in there. And Linux basically took a piecemeal namespace C-group approach to like stick it together and have all these composable pieces, and then eventually Windows added those things as well. What happened is that in the market, we have a thing that is really good at packaging up containers, and that is a tool chain called Docker. So at the end of the day, there's this, what everybody thinks of in terms of largest market share is Docker, and that predominantly runs with a backend on Linux. So for most practical purposes, a container, as everybody describes them in all the blogs that you read, is a Docker image that's running on Linux.
Cool, thank you.
So the purpose of using an orchestrator is you've got an application, it's bundled up in a container, it's portable, and now you want to run it on maybe many copies of the application across the host. So then you bring in an orchestrator, and the most popular one these days is called Kubernetes. Many people say that it's one versus some of the other ones. There are a couple other ones out there that are still in use, but the vast majority of focus these days seems to be on Kubernetes. And it defines, in addition to where the scheduling the containers to run on a particular host, it defines how they can communicate via network using some kind of proxying system, and then it allows you to scale up and down the number of copies of the application dynamically. Now, containers have gotten really popular in the past few years, and so a lot of, one of the really awesome things about containers from the beginning is they're super easy for a developer to use. You go in and you want to run some application and you do this Docker build command and Docker run, and suddenly you've got the ability to run any application in this packaged format wherever you want. It's a really nice experience. But as those containers have been moved into production, what they found is that there's actually, what we found and what other people have found is that there's actually some operational changes that you have to make, and there's some challenges that we'll talk about. So one of the things is, before you dealt with Linux operating systems that could auto-update when they needed security patches. And now the container is an immutable package of your stuff. And so if there's a security vulnerability, you have to rebuild your container. You have to monitor it differently. The idea of deploying as an immutable artifact is just a different experience. And what that means is you have to put a lot more focus on your build tooling versus configuration management or operational tooling. And that's a change that's happened. And what we discovered as we started using containers behind a lot of our services in the Oracle Cloud is that the advantage of having this great way for developers to build containers actually leads to some problems. And the problems are around developers without an operational mindset building. It kind of becomes the wild, wild west. Everybody's building things differently. You have these crazy images that no one knows how to make them again. You don't know what security vulnerabilities might be in them. They'll treat it like a virtual machine and just throw a bunch of applications inside the container, which sort of is the worst of both worlds. You have all of your applications bundled in the container, but you have no way to update them. And you end up with these giant 3-4 gigabyte containers, and people aren't really paying attention to how to handle security vulnerabilities.
And they bake all of their configuration into the image as well.
And so basically, when we started analyzing this at Oracle, we realized that the idea of a container is really valuable. It's super useful for packaging stuff up and shipping it around, but we needed some best practices to kind of combat these worst practices that developers were using. And in many ways, you can do that through policy. You can say, okay, we're going to build all our containers from this base image, we're going to put them all in CI/CD. So there's a lot that you can do that way, but as a developer, and what I've seen in other developers, if you don't make something easy and build a tool around it, then people won't follow your policies. So we decided if we're going to actually create a change and have all the developers using these new tools, following these new policies, we had to create tools around them. And so we built some internal tools, and then we thought, hey, these are really valuable, we'd like to get them out to the community, and so we packaged them up, cleaned them up, and then made them open source. So actually these are now available on GitHub, and the rest of this talk will be about a couple of the tools. So there's 3 of them. You can't really see that very well, I'm sorry about that. There's Smith, got nice logos, but you can't read the text. Smith, Railcar, and Crashcart. So Smith, which is the first tool that we're going to talk about, is a way to build what we call a microcontainer. So I mentioned you want to have containers, but you want to have policy around how to build the container. So this allows you to build a container that's still just a normal Docker container, but it adheres to a certain policy about what goes into the container and how it's built. And then Railcar is a debugging tool to help you debug containers that are running. And then Crashcart is an alternative container runtime that's kind of a research project to help make the container ecosystem a little bit more consistent. Do you have something yet? Okay. So I mentioned microcontainers when I was talking about this. So what's a microcontainer? You want to talk about what a microcontainer is?
Sure, I'd love to talk about what a microcontainer is. Apparently, it's a whale in a bottle. Go back to that. It's a fun logo. So like ship in a bottle, whale in a bottle. It's better. That's what that is. It's strictly better to have a whale in a bottle.
Yeah.
Okay, go for it. So basically, as Fish mentioned, we try to have smaller images. Like the goal here is that we need to be able to pull images much faster because we're going to be generating a lot of them. And if we generated a lot of them that are all 1 gig, we have a bunch to store. It's going to take longer to pull to all the network locations that we want to have. If they're large and bloated, they have, oh yes, they have a banana. Instead of just the banana, I have the jungle and the 800-pound gorilla to go along with all of that. I have all of this surface area inside my container of a bunch of things that I don't know what's in there, and I now have to figure out how to patch all of those things and understand whether or not I'm in compliance or not. So that's what's wrong with, people generating container images like their VM images, right? Like, along with the notion of, oh, I don't know, maybe there's systemd in there, or there's runit in there, to some other kind of supervisor and multiple processes. It's really not what you want to have going. So we really wanted people to focus on their application and what goes inside their container for that. So a microcontainer contains only what is absolutely necessary to run your application. It's a simplification of what we're trying to talk about. And in general, a single executable and just its dependencies. So if the process were Apache HTTPD, we really just want the HTTPD binary and libc and any of the other dependencies that are along with that. Just because it says single executable doesn't mean you can't fork an exec inside your container. The goal is it's only really about what you can contain, what you need to run your application. Second to that, in the same way we treat container images as immutable pieces of infrastructure, we also want to treat the file system in there as read-only. So basically, you shouldn't be going around and writing to arbitrary locations inside your container. That's an anti-pattern. You should really be writing to well-known locations that are probably volume-mounted into your container.
And this, just to add, this prevents the case that you see sometimes in production where someone goes into a container and starts modifying stuff in the container, and then you've got this great immutable infrastructure that suddenly you can't manage anymore because you've got 5 different versions of it. So this really enforces that people use operational practices.
Yes. If you found yourself in a Docker container typing apt-get install while it's running, you've lost the game, right? Like, so we really wanted to prevent people from doing that. And then also, we wanted to be able to run our applications as not root, even inside the container, even if there's isolation there, we really want it to not be a root process, the root user. So we want it to be all a particular user, and we want to be able to, if possible for the application, drop those privileges.
So it turns out that the idea of the user system in Linux is great for isolation, but if you're already using a containerization system to isolate, you don't need multiple users in the container, and it just adds extra overhead. So this is kind of stripping out some of the older Unix principles and replacing them with containerization and trying to make the container as simple as possible.
So as a result, we can post-process your image to only contain exactly what you need to run your application. That means that you have fewer layers, or most of the time in our case, exactly 1 layer, and then you can actually audit what is in there to know whether or not you're vulnerable and whether or not there's probability of an attack. So you don't need to have bash in there for somebody to run arbitrary commands against you if there was a vulnerability in your application. So
that explains this. Everybody follow the idea of a microcontainer. There's actually a blog post linked in these slides, which are up on SlideShare, and we'll make sure everybody has access to them, that talks in a lot more detail about what a microcontainer is and why we created the concept. But I thought it might be nice for you to see how one would build one. So, okay, let's see. Is that big enough? Do I need to go bigger?
Can you make it bigger, please? That's better.
Okay. We'll see if we can actually do stuff. Okay, so basically, Smith is just a simple command line utility. Very few options. And the idea is that you have a container definition that's just a YAML file. I'll open it up VI so that it's color-coded. So Smith actually functions in two different ways. You can build as your source from RPMs, or you can build as your source from other containers. We started out using RPMs, and for our use case inside of Oracle is really valuable because all of Oracle Linux is built off of the Fedora, Red Hat, CentOS ecosystem and uses RPMs. So we figured, why bother with actually even having Docker installed and when you can just take the RPM as the source of your application and then kind of convert it into a container. And that's great if you happen to be in that ecosystem, but of course Docker is broadly usable, and other people are using Debian or Ubuntu or Alpine or any other flavor of Linux, and so we thought, how do we extend it? And we could have gone and supported Debian using Debootstrap or something like that, but we figured, hey, what if you could just actually minimize an existing Docker container? So you could go and build with your existing tool set, Docker build for development, and then when you go to productize the container, or productionize the container, productize isn't a good word.
I mean, it could be a product. I'm not going to prevent people from doing that.
You can kind of shrink it down and just pull out the stuff that you need. So this is an example of the RPM-based build. So this basically says, make sure the core utils package is installed, pull out user bin cat, and then the command in the container will be user bin cat and then read data. And there's a directory here called rootfs, and this is automatically overlaid with the container, so you can see that it's just read and read data in there. And just run Smith. And so essentially what it's doing here is it's using a package called mock, which is Fedora's package for building and installing RPMs in an isolated environment. So it's very similar to starting a container and then running yum install and doing it, but it just has a very nice way where you can specify other yum repositories automatically on your system, and there it's done. So basically what that just did is build a container that has just the cat binary in it. And of course, that is very small. In fact, it's only 930K. So instead of having, like the smallest container you'll see based even on Alpine, which are the really small ones, are going to be about 20 megs. So we've got a container here that's 930K and it can run cat. Now, obviously running cat isn't super useful, so probably you'd want to do something a little bit more than just running cat. And so I have another example, and I've actually written a blog post about the construction of this YAML file because it's a little bit more complicated, and I can't go through it in the demo because it's a little bit too long of how I got to this point, but the blog post, which will be linked, has a whole bunch of information on how you go through building a more complicated container. So this is running Apache HTTPD in a container. And Apache HTTPD is a really good example of something that's a little bit more difficult. And the reason is because one of the really nice things that Smith does for you is when you specify a binary to pull out, it automatically gets all the static dependencies of that binary. So any SO file, so libc, etc., pthread.so, everything like that will be pulled out for you, so you don't have to go figure out everything that's linking to. But there are a couple of exceptions. One is it doesn't pull in configuration files for you, so you're going to have to specify those yourself. And if you DL open any binary, so you DL open a dynamic link library, it's not going to find that for you, so you have to pull those in. And HTTPT is an example of one that has some trickiness around it. So another thing that it does is it needs to drop privileges and change users. So you'll see this is a little bit more complicated. But even so, it's a fairly straightforward, I mean, it's pretty easy to read. So it starts from, it's actually taking the Docker HTTPD image off of Docker Hub. And then it's saying pull out HTTPD, and then of course these are the dynamic dependencies that it DL opens, and then these are modules that you would want to load. So you specify the modules that you want, and then the command is HTTPD. And other than that, that's pretty straightforward. And we can actually do...
can you go back to...
Sure.
So the dynamic dependencies, like in a lib RT, are those from the modules themselves, or that's from the...
In this case, it can be either. Yeah. So if the module is, the requirement is that it's DL open. So if the module, so these modules down here, if they are actually linked in the ELF headers to another library, it'll pull in those automatically. But if it DL opens another library via string, then those are ones you have to include.
So typically Apache is going to open, do a DL open on those modules at runtime.
Right.
They're enabled, but what it's saying is like once you put as a module, you put the .so file.
Yeah.
Smith is going to read that and automatically, if I understood correctly,
Yep,
it's going to do that. But if that module in turn have
Yep, it'll recursively walk until it finds everything in the dependency tree.
Strictly speaking, it's just running LDD, or the equivalent of LDD, on every ELF file that it finds.
Yeah. An example of building with this one is also pretty straightforward. Let me give it a new name. And you can see what it's doing here is it's actually downloading the image off of Docker Hub. And this image, of course, has a whole bunch of layers built into it because it's based off of, I think Ubuntu. I can't remember what the base image is. So it pulls all the layers. It pulls out the stuff. And then you can see right here, 1.8 megs for this result. Now, the original image on Docker Hub is about 100 megs. So, and it's so basically, and that's, someone went through and actually tried to make that as small as they absolutely could, and they still could only get to about 100 megs, and here we've gotten it down to 1.8, so it's like a 95% reduction in size. And just to kind of show you, so I have the two here. So I've written a little function that just basically takes an image and shows me the layers in it. So if I haven't broken it, this should actually kind of print out all the layers. So you can see scrolled off the screen because the screen's kind of small, but it's got a whole bunch of layers in there. And then if I want to do the same thing for my version, layers. So it's a single layer. And if we wanted to look at, is it called fcount?
Fcount.
Thanks, fcount. Let's just look at the number of files. So this is something that will essentially unpack all the layers and then count the number of lines in the tar gzip of each layer. So it's got about 3,000 files in there. Who knows what's in there? And then in my version, 79 files. So that's pretty easy to audit. So if you need to go figure out what's going wrong, you've only got 79 files that you need to check. The other thing that's really nice is Smith will build the exact same image SHA from the same source every time. And so, and this is true whether you're building from an RPM or another Docker image. So you can actually have, for example, continuous integration building the container constantly, and if it ever changes, if your ID, if your SHA ever changes, you know that the bits on disk in your image actually changed. So if something goes and updates libSSL and you're not using libSSL, it doesn't matter. But if you are using libSSL, you'll see that your thing is changing. You can know that it's time to retrigger. So it's just a nice way of checking to see if anything has been updated.
And when you're building with RPMs, you get a manifest of all of the dependencies and the versions of the RPMs that were included, so you can be able to go back and track back through for compatibility. If somebody's trying to check what version of that RPM did you have as your base, you're able to audit that directly.
Right, which is one of the other advantages of using the RPM version. So that's Smith. Does that make sense? It's on GitHub. You can go download it and try it out, fool around, contribute, post issues, whatever. So there is one drawback. Yeah.
No, sorry.
There is one drawback to Smith, and that is, well, it's not Smith. It's actually a drawback to using microcontainers. Generally, if you have an image that has a whole bunch of tools in it, it's really useful for debugging. And in fact, even for development, which is why I say that maybe the best thing to do is to start with a big container during the development and then shrink it down at the end, because you want to be able to go in there and figure out when things are going wrong. But the problem is, if you're in production, you've got this microized container, you need to go debug a problem. So let's take an example. Let's just launch. Okay, so I just launched my Docker container. I should have done that in a different window, so we'll just go over here.
Just so there's no confusion, these are some like aliases that he's written around Docker commands.
So drun, this is what I did. I did Docker run, exposing a port, read-only root file system, mounted a tempfs, mounted a read directory, and then just to prove that it works. Okay, it works. And then if I wanted to, I can't remember the name of my alias now. It's the problem with making aliases. Rewrite. So I could do this little sed statement, which you can see in there. I've gone ahead and exposed the directory that Apache is serving via volume, which is a nice kind of thing that we recommend with microcontainers, where you have your config files in a read directory and then your output files like logging, etc., in a write directory, so that if you need to get to it from the host. So basically,
you misspelled rewrite, so it's rewrite, no I. No, one more back. T.
Thank you.
No.
Read.
E-E. T-E. Got it.
Oh, I misspelled the alias. That's
Yeah.
even better. I missed that. Oops. Curl. So basically, I edited a local file that's not in the container to change what's inside it. Okay, but let's say this container is running and something goes wrong. And we want to figure out, say, let's do some networking introspection. So let's do netstat. Let's see where it's listening. Thank you.
So basically, like, maybe you're being DDoSed or you want to see all those things, and you're going to look at it from the root container outside of the host. And so you're going to look for that. And here you can see that there's not HTTPD that's running, but because you did a Docker expose, you actually have Docker proxy that's actually there. And the networking stack inside of the container is actually what you would want to do. So you need to go inspect that. If you're using, the wrong kind of container image, you would Docker exec, right?
Docker exec. dpid.
Or DID, sorry.
Yeah, did. Thank you. Oh no, it didn't work.
Well, you don't have netstat in there because we told you not to put any tools inside there except your application. So now what are you going to do? Now, the good news is that Linux has this command nsenter, which allows you to arbitrarily enter either specific namespaces or all of the namespaces of a given, in this example, you can specify the particular target. So here you can say the target of the process, so dpid is just a way to grab the current PID of the HPD daemon running inside of that container, and then Vish can enter -n for the network namespace, and then run nsenter, or netstat, sorry, and see all of the information.
What did I do?
Failed first dash, and you need to,
No, it's dpid that failed.
yeah.
Okay, let's find the PID manually. Okay, there's one, 8554. I had a little helper to get the PID for me, but apparently I broke it. Okay, there we go. So this shows me, nsenter is great because we talked about namespaces being what containers are constructed out of. So this allows you to enter arbitrary namespaces. So for things like entering the network namespace, like I could TCP dump, I don't have to have netstat installed in the container. I can use the host version of netstat, but enter the namespace of the container and get information. So that's really cool.
But now, yeah, sorry. No, you go.
No, I was entering you with
intro. But now what if I wanted to know what open files that process had open? So normally I would use outside of the container LSOF, and I would grep for HTTPD to see everything that it's doing.
Oh, I should bless this because it's going to be really cool.
And so here we have all of the results. But as you can see, it says, oh, you're opening libnss files from there, but then it says that it can't stat that file, so we can't know anything about the size of the file or the user ID or any of that information because it can't find it. And the reason it can't find it is because LSOF is running outside of the container, and those files only exist inside the container. So what if we tried to run LSOF with netstat, or with not netstat, nsenter? They're too close together. So Vish is changing it to join the file system namespace, the mount namespace.
We'll try it. LSOF. Grep. HTTP.
Oh.
Crap. There's no LSOF in the container. Same problem.
So now what are we going to do? The LSOF from the root container or the host OS can't work against the containerized process, and we've prevented it from being inside the container. What are we going to do? Thus enters our other tool, Crashcart, which is essentially like plugging in the KVM to the rack and like logging into the box that's unable to be accessed through other means, except for we're doing it with a container here. So basically, Vish is going to run Crashcart against the process, And Crashcart is going to sneakernet its way in and add some extra files into the mount namespace, into the container namespace, such that we can have the tool LSOF.
So I need a path. Now, if I just run Crashcart by itself, it'll just give me a shell inside the container, which is pretty cool because there's no shell in the container. So you might think about how we did that. And maybe we'll have time to talk about it. But if I want to execute an actual binary in there, then I can pass the full path to the binary as well. So dev Crashcart bin LSOF, I think is where it is.
Yeah.
And there we go.
Ta-da!
That's less of it.
It works, like we said it did. So now we can stat all the files, we can see what they are, and basically the premise is you didn't know what was going to be inside that container when you need to go to debug it, but you can bring it along with you when you're ready. And so you can just make it work for any kind of container a priori without knowing anything about what's inside that container.
And the great thing is you can run this after you've already run a container. So you can have a Docker container running for a week and then say, oh, I need to go figure out what's going on. You can put Crashcart on there and run this stuff in there. You can also do it without taking the container down and restarting it. So if something goes wrong in the container and you need to debug it as it is right in that state, then you can do it. A lot of the other methods would involve restarting it with a volume mount, etc.
Yeah. Some things only go wrong in production. And so this is the tool that allows you to get there while it's happening.
So it might be interesting to just briefly talk about why this is difficult. So why do we have to have a tool for this? And the issue is around the security of namespaces. So the basic problem is you have a file system namespace inside your container with all of its own isolated dependencies. You want to run other processes inside that namespace. And a lot of these tools that are built on Linux with C are dynamically linked, so you don't necessarily have a single executable that you could just copy into the container and run. And so you need to mount not just the executable in the container, but for example, libc and all of the dependencies of that thing.
So what you're saying is we told everybody to build really small containers and run them really securely, and then here's a way to go violate all of that security.
Right, but only while you're debugging.
Oh, that's fantastic.
And the fact is, when you exit Crashcart, it removes the mount, so you don't leave anything behind in the container. Because remember, the container's got a read-only file system, so you're not messing with the container, you're just using it for introspection. And so what this required, and the reason this is somewhat complex and we needed to make a tool around it, is you need all of your tools built relocated. So you can't just load your, if you want it to work with any arbitrary container, you can't just load, for example, LSOF into the bin directory because there may be other stuff in the bin directory that you'd be clobbering, or it may not work with the version of libc that's installed in the container, etc. So we had to build a tool chain, and we used something called Nix, which you can look up. It's kind of a neat package manager to do that, so that everything's been relocated into dev Crashcart. So it's in a new location. All of the dependencies are there. Yeah.
Why is it in dev Crashcart?
That's a good question.
Thank you.
So we could have picked any location. We wanted to we had two requirements. One is we want to make sure it doesn't conflict with anything else that might be installed. So Nix, for example, installs in /Nix. So that would be kind of a useful place, except if the container itself was built with Nix, then it would conflict there. And secondly, the great thing about dev is that it tends to be read-write in most containers by default, and so it's an easy place to mount stuff versus just mounting it /Crashcart. So we picked /dev/Crashcart just as a nice location that was convenient, but it was somewhat arbitrary. So we have an image. Now the next thing that's hard is you can't actually take an existing mount namespace and mount something else in it in many cases because of security restrictions in Linux. And so we do this kind of fancy little dance where we put all of our dependencies into an ext3 file system. We mount it as a loopback device on the host. We mount the dev inside the container without entering the other namespaces. And then we, from there, are able to bind mount to a different location of the file system. There are other ways of doing this that are a little bit simpler, but they always require you doing something specific when you start the container the first time. So you can't go in and have a container that's been running for a week and then go and debug it. You'd have to specifically start it with the mount set up in a way so that you can mount stuff into it. So we do this trickiness, which ultimately, it would be great if it could be removed, but it would require some changes in the Linux kernel to actually get there. And even if those changes were made today, it's going to be a couple of years before anybody can use them. So we figured we needed a way to work around this stuff. Yeah, so that's Smith and Crashcart. Let me pop back to the,
Command enter.
Shift Command Enter, put it on the page that we're on. Oh, did it?
Okay.
Sweet. So as I said, some links about blogs and link to the code and articles. You don't necessarily need a picture of those because we're going to give you the slides later, but if you're curious. And then finally, before we get to questions, legal says I have to put this up.
Do not take anything of what we said as being real.
I think this is designed for people that are talking about actual Oracle products, which we're not. So, but they say we have to include it. So, yeah. So, questions and answers.
You asked your question. Please.
I'm just curious if there's any kind of published roadmap for Smith or what's coming next.
It's at this point it's somewhat up to the community. So we got what we needed out of it in terms of internal at Oracle, and we wanted other people to start using it. There's some things that I would like to see happen. I would like some of the features to actually be merged into Docker. One of the reasons we picked Go for that particular binary is because all of the other container ecosystem is in Go, and so we could pull aspects out of it into Docker. So for example, Docker build grew about a year ago an option called -- squash, which is partially on the way to what we were doing. And the reason that grew is because there was an external project called Docker Squash that everybody started using, and so they put it in as an option. I would love to have, for example, in the multi-stage build, an option of pulling out dependencies automatically, etc., in there. And I think it could be done fairly easily. The code's already here, so it would just be a matter of kind of working with the community and get that stuff in.
Yeah, and we conceived of all of this and executed on all of this before multi-stage builds came into being. So I still recommend everybody use multi-stage builds, but this is a last, after you've done that, still run this over it just to make sure that you have what you need.
So other than that, we haven't really had any requests for features. There were some requests on the Railcar side, which is the project we didn't talk about, and we've been trying to move forward on some of those. We don't have a lot of resources at Oracle to work on this stuff, unfortunately. I mean, sorry, to work on this particular project.
Yeah. For Crashcart, there are some things that we're working on, particularly because I want to use it with all of our Kubernetes stuff. So Crashcart attaches to a running container. If you're using an orchestration environment like Kubernetes, you can have many containers that are on any piece of infrastructure that represent your cluster. So we basically want to be able to kind of give you Crashcart with a K that allows you to specify a particular pod and a container in that pod to go attach remotely to that. So that it just like wires up all the stuff that you need to do that thing. But that's coming soon to a GitHub repo near you.
I think that Crashcart could be a useful piece of infrastructure if anybody ever gets to the point where they're providing containers as a service in a multi-tenant environment. So one of the issues today with running containers is you really need access to the host. There's some things that, debugging especially, where you have to be able to have access to the host. And if you're running in a multi-tenant environment, if you ever get to the point where we've decided that containers are secure enough to allow that, he says never, I say maybe someday. If we ever get to that point, then you're going to need a way to get into, it would be nice to have a way to get into the containers that doesn't require you installing, for example, an SSH daemon inside your container. And you could imagine a world where you could kind of hook Crashcart up to a little utility that could let you SSH. It could enter the namespace of the container and start up SSH so you could get into it, for example. So it'd be kind of like a side way to get into the container when the utilities aren't there.
We don't need SSH. It's already a binary that we can exec. We can just attach that PTY to something else. So you don't really need SSH.
True. Yeah.
So,
Anyway, you could. Yeah.
Yeah.
Technical babble. Good point. Yeah. Any other questions?
Yeah. So, do you find that as you try to package only the minimum amount of files, that you also need to modify, like, in addition to adding the configuration files, like, for example, when Apache by default creates the logs, then you need to kind of modify a bunch of other things to get it to work, other than listing the...
In general, you do. And so I mentioned that we have this kind of set of rules where we have a read directory and a write directory. In general, the goal is to make things log out to standard out so that they fit in with the Docker logging infrastructure. But that doesn't always work. Sometimes you have multiple logs and you have to put them in a directory. So we tend to put all those in a right directory. And that can be a little bit tricky, but you can do a lot of fun things with symlinks that help make it easier. You don't actually have to change all the config to write to the right place. You can just symlink into the right directory.
Or things like writing the PID and
The pin files.
Yeah. So we have, for example, again, one of the standards is you have a run directory that's a tempfs, and I actually created that when I ran with the Docker command, and that's where all the temporary stuff goes.
And have you measured, like, is there an impact, for example, also on the diminished size? Is there an impact on the startup of the containers? Like, is it meaningful or?
Startup only if you're including polling and the extra the overlay, the instantiation of another overlay. You only have one layer that needs to be synthesized. So
yeah, if you're for startup, if you're including poll, it's huge. If you're not including poll, there still is the instantiation, depending on the backend you're using, that can be slower or faster.
Yeah, if it's like, it's, at the end of the day, you're removing all the funds, but they're not being used. It's starting the same process. But I don't know if there's any other thing that. The reason why I'm asking this is to give you the context is we also have like a serverless product that we're working on that instantiates the containers, and anything that makes that quicker is a big win.
Yep.
Yeah. So. Just a little bit of, we didn't get into Railcar, but a little bit of things we discovered while working on Railcar, which is an alternative container runtime. That's all built in Rust, and it's designed to be very fast. And I was assuming it was actually going to be quite a bit faster than Run C, which is the default runtime, because that's pretty slow. But it turns out that there's two things that are the slow part that have nothing to do with the bit of code that's in the runtime. The first thing is the callbacks for the network. So the callback to libnetwork to set up the network tends to take a bunch of time. And that needs to happen unless you have an alternative way around having to do that. So the exec, there's things called the pre-exec and the post-exec hooks that Docker currently only uses the libnetwork one. But that's shelling out to another process to do stuff. It's very convenient because it's easy, but it's kind of slow. And the other thing actually is slowness in the kernel. So for example, taking out the libnetwork stuff, we were seeing launch times of about 200 to 300 milliseconds, sometimes down to 100 to 150 milliseconds, which seems quite slow. And this was on a totally unloaded system, so you would think you could actually get quite a bit faster than that, because it's basically just making a bunch of syscalls and then execing. It turns out that the vast majority of the time is spent in the kernel waiting on locks, and the locks are around creating the network namespace is very slow, takes like 50 to 60 milliseconds, and entering the C groups takes 50 to 60 milliseconds. Which leads to one conclusion. If you pre-create the network namespace, or all the namespaces, but specifically the network namespace, and pre-create the C groups and just enter them all at the end, then you can get your container launch down to about 3 milliseconds, which is the fastest we saw. Now, unfortunately, you don't have the knobs to be able to do that in Docker, so you have to do a little bit of hacking with either Run C directly or the container runtime directly, but I think it's possible to get it down fairly low. Of course, that's dwarfed by the image pulling and stuff like that, which tends to be the big bottleneck. And then, of course,
and the word you have a worst case, right? So if you slab allocate 100 of them, and you run out of all of those, right? Like you're in a serverless product, and all of a sudden you launch 100 of those Lambda functions, right? Then you still have to wait for the rest of those to get spun up. So your worst case scenario, your outliers for that product, are still going to be all of that locking in the kernel.
Yeah, I mean, you can do like some of the algorithm, like Apache, you have this pool of pre-created.
Yeah, but you still have to prepare for the worst case scenario where you've bursted into all of that, right? Like you're either going to induce queuing and latency for the request, or you're going to hit latency when you're actually you've run out of all of it and you've got to go create it.
I mean, yes, you allocate everything if you want to optimize for that. Like some of the algorithm is that the more that you are serving that you see that it's growing, the more that you start kind of in the background.
Yeah, except for you're in a serverless product which is meant to be utility-based computing, and the more you pre-create, the less cost efficiency you have in your product.
Yeah, that's the trade-off, right? If you want to plan for the worst case scenario, then you need to.
We spent some time actually trying to optimize that path, and then we realized that it's dwarfed by the startup of the thing running in the container. So for example, even the Python execution time is not super fast, especially if you're loading something really complicated like, say, TensorFlow, which is got like 500 megabytes of Python files that it's loading, that itself can be quite slow. And if you're running Java, you've got 400 milliseconds for the JVM to start up. So even if you fully optimize the container start time, unless you're running a static binary inside the container that's small, you're going to waste a bunch of time there. And so you end up having to go with the pre-creation route anyway to work around that problem.
Yeah.
So
The other question I have, I don't know how much time we have, is like, for Apache HTTP is relatively clear, but you have this complex application which Python a bunch of modules, and you need to go manually figure out, which they use. There are some other techniques, other tools. What they do is you just run that for a production workload. Take a look at which files got access and package stuff.
Yeah, I think there's something called CDE which actually does exactly that. But you run something, it sees every file touch, and it gives you a list of them.
Like a few of those. Have you look at those as some of the drawbacks versus
yeah, I mean,
a way of combining them? Or?
There probably would be. I mean, at the very least, you could use one of those tools and then output your Smith file with specific things. For things like scripting languages, my general opinion is that in order to be safe, you probably want to do it in something like a virtual environment, Python, where it packages everything up for you and you just copy the whole thing. Because trying to find all the little tools in the various directories they can be in when it's a bunch of Python files is tough. But I'm curious to see if anybody's actually tried using that approach for anything beyond a tool, like in production, because I think it's a reasonable idea, but I would be a bit concerned that your test coverage is not.
Yeah, there are some companies that did it for VM migration. That's what I first ran into those to kind of identify, but yeah.
Yeah, basically it's a whack-a-mole process, right? When you start getting, if you're from the Java ecosystem, you're used to like, oh, I'm going to do an uber jar and then I'm going to shade things out, and then all of a sudden in production you shaded out the method that you actually needed, right? Like, so the process is the same. We're just trying to codify it from a container. If you go too wide with your machete through your container image, then you're lucky if the application just doesn't start up at the beginning. Worst case scenario, you're waiting for some code path to get hit that isn't hit all the time, and then you get a method not found kind of scenario.
Yeah, you find that.
Yeah. Yeah, and so really the goal is, the policy would be, if your thing is Python or Java or Node or Ruby, you include all of that, but it's just everything else that's not necessary as related to that you have to be able to find. And that's kind of the rule of thumb. And like, if that's still too big, then you probably don't have a microservice that actually should be packaged in a container, and you need to step back. If you're in the VM to container mode, that's a God bless you for trying that. That's a long road to hoe. And
what we've discovered is that there are some ecosystems that are easier to deal with, and the kind of basic Linux, Unix philosophy of a bunch of small things tend to be easy to pull stuff out, whereas there are other things which are giant monolithic tools that use a lot. And the particular example I've been dealing with lately is trying to get, for example, a microized TensorFlow container. It uses a lot of dependencies and a lot of different languages, and the basic containers are like 3.5, 4 gigs, and so it seems like, hey, this would be a great target to really minimize this, but the complexity goes way up when you've got a tool chain like that. On the development side, it doesn't matter, you're pulling everything in. When you try and take that into production, then you have to have a way to shrink it down. And sometimes it means dealing with the ecosystem and finding a different solution in the ecosystem to start with before you go into microization. So it's not universal. You can't just take any arbitrary container and use Smith and figure it out. Sometimes
it's not magic?
It's not magic. You actually have to think about things sometimes.
I'm only going to a meetup with you when you sell magic next time.
Okay, next time, magic. We can obviously do more questions, but I think our time's up, so why don't we just stop the official discussion now, and then we can talk in person. We'll be here, you're here, without the microphone. So